good things to tell you about, so if it goes a little bit long, forgive me, but there really is a lot of positive things to say. Many of you have been here. I recognize you from previous years, but I'm just going to give you just that really quick rundown to get everyone oriented to why we're here. Obviously, we're here because of the amazing work and vision of the Silva family. So first, let's give it up for them. Doing drug discovery and pushing the needle on diseases is a partnership. Clinical people, scientific people, but patients as well. It's the patients and the families and the caregivers that inspire us to do better, to go to work and make this a better situation for our patients. So we would not be able to do what we do without all of you partnering with us. So thank you very much for doing that. So all of these diseases that happen to us, often when we get older, diseases like Alzheimer's, Parkinson's disease, but sometimes when you have a strong gene mutation, they can come on earlier, and ataxia is an example of that kind of disease when it runs in the family. A lot of these diseases of the brain are diseases in which proteins fold into the wrong shape. I think we've mentioned that before, but for those of you who haven't heard me before, I just wanted to remind you that these diseases are all linked with this common biological problem that proteins accumulate and eventually they become toxic, especially to cells in the body that do not replicate. And in the brain, we need our cells not to replicate because those are the precious cells that keep our lifelong memories of how we ride a bike, of who our family are. We can't keep turning those cells over like skin. And so when these proteins go rogue, they don't affect your skin, but they affect your brain. And that's why we deal with these terrible diseases as we age. So they're all linked in this common way. Now, the field has come together and said if these is caused by a toxic protein, then one thing we can do is we can reduce the levels of that toxic protein. It's a very obvious, reasonable place to start. And this is based on 100 years of work in pathology and 20 to 30 years work on human genetics has kind of told us these proteins are really important. And on September the 27th this year, we got some news that an antibody made by Biogen and Eisai finally shifted the needle on Alzheimer's disease. That is huge news. Now you'll see when you read about that people are rightfully saying that this was a small effect. It was like a 30% reduction in the progression, but that was over 1 year. And we can certainly do better. But we have not, in 20 years of trials, ever seen data like that before. And I think that gives the whole field a lot of hope. We're seeing the first ALS gene therapies that looked, like they were maybe working in the first part of the trial. As those patients have been followed, those gene therapies that are also reducing toxic proteins are starting to show some benefit. Okay, this is really amazing news that slowly, after decades of clinical trials, we're slowly starting to see that the tide is turning for these diseases. That does not mean the battle's over. I gave a talk this week at New York at the New York Stem Cell Foundation, and one of the things I talked about was cancer and the long journey that the cancer field has gone through. There are amazing stories in cancer, but as many of you will know, there's still so much to do. The first cancer chemotherapy, believe it or not, was in the Second World War, was mustard gas. When it was observed when mustard gas was leaking, people had a damage to the way their blood cells proliferated. And some really smart people who were observing this said, well, if it can cause this kind of toxicity, maybe for people who have blood cell tumors, mustard gas and its derivative compounds could actually be a chemotherapy. That was the birth of chemotherapy, and that was in the 1940s. We haven't beaten cancer yet, okay, but I think we just at least had our mustard gas moment for neurodegenerative diseases. So there are two basic ways of tackling this, reducing the proteins. There's ways in which you can use, for example, antibodies, and that's what they did with the Alzheimer's therapy. And then there's ways we can use gene therapies to actually go in and manipulate the genes. And we're interested in all of those types of approaches. And companies are really getting born now and really pushing the envelope on what we can do with these kinds of therapies. I don't know where my wife is, but she's heading the neuroscience program at a company called Arbor. And last year I told you about a technology called CRISPR, where you can go in and fix genes with scissors. Well, Arbor is now taking that technology into the clinic, and she's leading their neurologic disease program. So this is really an amazing moment. So we're seeing this happen now, and it's really quite amazing. There are therapies that are not working too. There are therapies that are going into trial. These therapies that are designed to decrease the levels of these proteins, and we're seeing some failures. The Huntington's disease trials haven't succeeded yet, but there's hope because we've started to see some clues about why they weren't working and what we can look for. So we're taking, with your support, we're taking two basic approaches now to address this. Because therapies are actually appearing now, which is really amazing. This was not happening when we started, when we started this fundraiser a few years ago. I wasn't coming up to you and saying, therapies are now hitting us from left, right, and center from drug companies. Well, they are now, which is an amazing achievement. So our first aim is really clinical. I'm actually trying to build what I'm calling a clinical trial ready cohort for different groups of patients at Brigham and Women's, so that when we see patients in the clinic, we're tracking them and getting them ready for clinical trials that are around the corner. So we can tell companies that we have patients where we've tracked their biomarkers, we've looked at their biometrics, we've got their imaging. So if you want to test therapies on our patients, we've got a cohort that's ready to go. So that's called a clinical trial ready cohort. We've chosen 3 groups of patients for that. Patients with diseases of synuclein, which is diseases like Parkinson's disease, patients who have familial forms of diseases with synuclein, Parkinson's disease, and thanks to you, the third category is going to be spinocerebellar ataxia type 3. And the second thing we're doing, which is in the basic science part of what we're doing, is we're making stem cells from our patients. So we're not just taking their biomarkers, we're actually growing avatars of our patients in the dish. We take a skin biopsy, we turn it into an embryonic stem cell-like cell, and then we grow brain cells from the patients so that we can figure out if a patient responds to a drug or doesn't respond to a drug. Could we have predicted that in the dish? That's really important because lots of trials go and they fail, but some of those patients may actually have benefited. And we need to know why some patients are benefiting and why some people are not. So we took an ataxia that's called multiple system atrophy, which is a terrible disease that doesn't even have a gene attached to it. And we've actually, in the last year since I've talked to you, we completed our first clinical trial for MSA in our department. And what we found was that some patients, we had a PET scan that responded to the drug. Some patients responded beautifully to the drug. The whole inflammation in their brain cleared up, and other patients didn't respond at all. And we have no idea why, but those patients were presumably mixed by the drug companies that tried that drug, and that could be a really good explanation for why that drug failed in the clinic. There could truly have been responders. And so what I've done now is gone and taken skin biopsies from the patients who responded, who didn't respond, and we've now made in the dish the inflammatory cells from their brain in the lab so we can actually test the drug and see could we have predicted that or not. So this is a new way of doing business for clinical trials. It's really early days, and we really need support so that we can offer our patients not the placebo but the drug. We're going to say to them, we'll give you the drug and we'll use you as your own placebo because we'll have your history and figure out did you respond or not. That's what we really want to build for our patients, and with your support, I really hope one day we can get there. So I'm very excited about this. For the stem cell stuff, it's a lot of work. And so I've definitely needed to think about how we're going to make this program that you're all supporting more robust. And I've needed to recruit people to do this. And this last year, I've partnered up with a very talented young scientist who has been doing a gene therapy with me on a young boy with an ataxia. He's 14, his family's public with it, his name is Tayson, he lives in New York City, and he's progressing severely every year with a type of ataxia called DRPLA. My colleague Tim Yu at Children's Hospital designed an antisense oligonucleotide therapy just for him, and our lab, through a woman I'm going to introduce to you in a minute, has developed stem cell models for Tayson in the lab so that we can predict whether or not that therapy is going to help him. Okay, so this is really the way we want to start designing personalized medicine approaches for our patients. But I was so impressed with her, I asked her, would she consider leading a program more broadly, not just on his ataxia, but on other ataxias like SCA3 as well. And I said, why don't you put together an application and tell us what you need, and let's see if we can at least get you started. And I'm so thrilled that she's going to now be the inaugural Silva Family Scholar at Brigham and Women's Hospital. So she's allowed me to push forward the work on Veronica Silva and Mark Silva's cells. A year ago, yes, it's been a lot of work. We've been working on them for a few years. A year ago, we were trying to correct their gene mutation in the dish. There are no corrected lines like this in the world for spinocerebellar ataxia type 3. We hit a roadblock. You might remember it from last year. We were really struggling to overcome some technical difficulties. Well, we're not fully there yet, but I can say to you this, that we overcame those difficulties. The DNA from those cells is now sitting at the Garvan Institute in Australia. Literally last night, they told me that they have confirmed that the mutation is corrected, which is really great news. So we're hoping we can release these cells to the field. I don't want to overpromise yet. I've been burnt before with this stuff. There's 3 billion letters in the genome, and they are now going to look across the whole genome and make sure there's no strange rearrangements of the genome and that these cells are ready to go and can be used. But I hope to be standing here next year and tell you that we've released those cells to the community, and for the first time the ataxia community has a reagent that's incredibly important to them, because if you try a gene therapy and you lower these toxic proteins, you need to have a gold standard. You need to be able to look in the dish and say, my therapy did exactly what I would expect when you correct that gene mutation. But if you don't have the stem cells with the gene mutation corrected, you could never do that. So my wife and I created some of the first cells like this for Parkinson's disease more than a decade ago, and we have our first drugs in clinical trial now that have been tested on those cells. We hope to be able to do the same thing with these cells. So fingers crossed, pray for us that we get those done. So finally, if you don't mind, and I know it's going to be a little hard to hear, But the inaugural Silva family scholar's name is Asha Korecka. Asha is a Polish woman. She's an amazing scientist. She did her PhD in the Netherlands in the top neuroscience institute in Amsterdam. She then came to Harvard Medical School. She did her postdoctoral training in gene therapy. She developed some gene therapies for Parkinson's disease as a postdoctoral fellow. She's come to join me as a junior faculty member working on the gene therapy for that young boy, Tayson, and she's now going to oversee the genetic correction of the Silva family stem cell lines. So I'm going to let you hear from her. She's actually in Poland right now visiting her 101-year-old grandfather, but she recorded a video and it goes for a few minutes, so if you don't mind, she's going to teach a little bit about gene therapy and what she's doing, and thank you again for supporting us and supporting her. It makes a world of difference.